Hello and welcome. Today we will be taking a look at one of the most famous cycles in physics, and that is the Carnot cycle. So first off, what actually is the Carnot cycle? First proposed by French physicist Carnot in 1824, the Carnot cycle is an idealized model of a thermodynamic system for a heat engine. The Carnot cycle consists of the following four reversible processes operating between a hot and cold reservoir: isothermal expansion, adiabatic expansion, isothermal compression, and adiabatic compression. The cycle is reversible, which basically means that if we begin at some equilibrium state, the processes will take us back to that same state. These processes do not involve dissipative factors such as friction. We can construct the Carnot cycle with many different systems, but the concepts can be shown using a familiar working fluid, the ideal gas. The system can be regarded as a chamber enclosed by a piston and filled with this ideal gas.
Well, let me introduce the first part of the Carnot cycle, isothermal expansion. In this process, the ideal gas in the system absorbs heat from a heat source at a high temperature T. It expands and does work on the surroundings. First, the working substance contact with the source. The working substance in the engine touches the hot reservoir, and then the piston starts to move outward because of the gas expands at the same temperature. Because the heat is absorbed from the source, which is the hot reservoir, to keep T constant, the volume increases and the pressure increases while the T is kept at TH at constant.
The second process performed on the gas is an adiabatic expansion. During an adiabatic process, no heat is transferred to the gas. As the piston moves outwards, the pressure in the gas is lowered, and as a result, the temperature decreases and the volume increases as the gas expands to fill the volume.
As the gas pressure has decreased in the last process, note the piston will be pushed inward by the surrounding. This stage is called isothermal compression. The excess heat flows to the colder reservoir to keep the temperature unchanged, so the gas is compressed at constant temperature, while the pressure is increasing. Now we go to the last stage, the adiabatic compression.
In this stage, the cylinder is insulated and the gas is compressed adiabatically. This means that the volume decreases and the temperature and pressure both increase, without any heat transfer in or out of the system. The change in internal energy is equivalent to the work done by the engine. This is equal to the product of the number of moles of gas, the specific heat capacity of the gas at constant volume, and the change in temperature. The change in temperature is greater than zero as the temperature increases, so the change in internal energy is also greater than zero. The efficiency of a heat engine is defined as the ratio between the work produced by the engine and the absolute value of the heat from the hot reservoir. As the work produced is the same as the difference in heat into the system and out of it, the efficiency can be expressed as 1 minus the ratio of the heat expended to the cold reservoir to the heat from the hot reservoir. A thermal reservoir is a system that has a very large heat capacity, so its temperature effectively remains constant. It can be shown that in the Carnot engine, the ratio of the absolute values of the heat in and out of the system is equivalent to the ratio of the temperatures of the reservoirs. This is in principle done by expressing the heat transfer between the reservoirs as the negative of the integral of pressure with respect to volume. This is done by noticing that the work done and heat must be equivalent as the internal energy remains constant. Then, using the relations between the variables in an adiabatic process, this relation between ratios can be determined, yielding the expression for the efficiency of the Carnot engine as shown.
In summary, we can say that the Carnot cycle is a theoretical cycle that is the most efficient cyclical process possible. Any engine using the Carnot cycle, which uses only reversible processes, is known as a Carnot engine. While Carnot engines are ideal engines, in reality, no engine achieves Carnot's theoretical maximum efficiency, since dissipative processes, such as friction, plays a role. However, the Carnot cycle is still a highly useful benchmark to design any engine that produces net work output and can be used to improve upon modern engine efficiencies. Thank you for watching, and I hope this video helped you understand some of the initial concepts for the Carnot engine.